This is lecture number 16 in this course on electric machine design. So if you remember, in the last class we were talking about the output equations for the DC machines and AC machines, and I had asked you to derive the output equation for AC machines. I will assume that you would have studied that, and I will just mention the output equation here. The output equation for a DC machine, sorry, for AC machine is equal to Q in kVA is 1.11 times kW times total magnetic loading times total electric loading times ns, that is the synchronous speed, times 10 to the power minus 3 into 10 to the power minus 3. And when we substitute the values of the total magnetic loading and total electric loading, this comes out to be 1.11 times when we substitute the values and we simplify this further, this Q comes out to be C naught D square L ns, where C naught is equal to 11 times BAV, that is the total magnetic loading, times the AC electric loading times kW times 10 to the power minus 3, and this C naught is known as the output coefficient. Okay, so if you are interested, you can look up the books on you can refer to the textbook for this course, that is this AK Sawhney, and you can also refer to other machine books, books on electric machines like Nagrath Kothari, and you can derive this. Nothing too difficult in this derivation. So after we have derived this, we see that the output equation for the AC machine is C naught times D square L times ns. And if you recall, for the DC machines as well, we had a similar expression. The expression was for DC, it was C naught D square L n, right? The difference here is in the fact that the output coefficients are different for DC, and in case of AC, this ns is the synchronous speed. Okay, all right. So now moving forward, we will talk about the various factors influencing the size of the rotating machines. So if you see in both the output equations, you see that this d square by L and this ns and the speed, right? For the same output, if you have the same output Q, this factor d square L and n, they have a relation. So what is that relation? And let's see. Let's see what the relation is. We first talk about speed. Now if you see that this d square L is actually the diameter of the core and the length of the core, so this in effect is in the volume, right? So for the same output power, this C naught d square L ns, and for the same output power the volume and the speed are inversely related. What does that mean? If you have the same output, for the same output, the machine with higher speed will have a lower volume, and hence when the volume is lesser, the cost of this machine is less in comparison to another machine where this ns is low, which has in effect translates to a higher volume, and in effect this translates to higher cost. So this is when you have the same Q, this volume and speed have this inverse relation. So whenever there has to be a choice between this speed, when you don't have the speed specified, it is always better that you select the highest speed rating for any given power. However, a key thing to note here is that you cannot select the speeds arbitrarily. So an upper limit is set due to mechanical considerations. So these mechanical considerations have to be factored into the design process. Okay, so this was about the speed and volume. Next, we have the output coefficient. So again we come back to this equation, the output equation. We see that for the same power, the volume of the active parts is inversely proportional to the output coefficient. What does this mean? If you increase the value of this C naught, this means that your size will decrease and your cost will decrease. So from an economic point of view, what should be the ideal CO or the output coefficient? It should be high, as high as possible. Okay. So what is this CO in exactly? This CO, if you see for DC machines, it is pi square BAV AC into 10 to the power minus 3 for DC machines, and it is and this is 11 times BAV AC into 10 to the power minus 3 for AC. Or in general, if you want to write, you can write this CO as some constant K times BAV into AC. So where this K is some constant. Okay. So this CO is a product of the specific magnetic loading and the specific electric loading, right? So what happens? The size of the machine and hence the cost of the machine, the size of the machine and the cost of the machine decreases if you have a higher specific magnetic loading and a specific electric loading. Okay, from commercially or from an economic point of view, it is desirable to have these BAV and AC, that is the specific magnetic loading and the specific magnetic electric loading. These should be as high as possible. Okay, so also, so naturally, as you can, I think I show you, this is logical as well, you cannot increase these without bound, so there have to be some, you know, counter effects of increasing them without bound, so that the designer has to see whether, you know, temperature can be permitted without, I mean, temperature considerations allow us to increase these without bound. Okay, so these are some of the factors that the designer should keep in mind. Okay, so this is about the considerations of speed and the output coefficient in relation to the size of the size of the machine. So now let's solve some problems on whatever we have discussed so far. So let's say you have a question. You have a 350 kilowatt machine which is operating at 500 volts and has a speed of 450 rpm, and it is a 6-pole DC generator, and the armature diameter is 0.87 meter and the core length is 0.32 meters. The conductor number of conductors is 660, which is lap wound. Conductors. So you have to calculate the specific magnetic loading and the specific electric loading. Okay, so this is the question. Let's try and see how we solve it. So the first step that you're going to do is you will calculate your armature current. IA, and that current is, what is that current? That current is the power, which is power divided by voltage. So we have 350 into 10 to the power 3 divided by the voltage is 500, so this is going to be 700 ampere. This is the armature current IA. Now the current in each conductor current in each conductor IZ is equal to IA by A, so that is equal to 700 divided by 6. So this comes out to be 116.66 amperes, since A is equal to P for a lap winding. This is from your machines course. Now the specific electric loading AC is equal to IZ times Z divided by pi D, and when you substitute these values, this comes out to be 28200 ampere conductors per meter. Okay, so this is the specific electric loading. And when you talk about the EMF, that is phi Zn P over A, we have already seen this equation in the previous lecture. So the flux per pole phi is equal to E into A divided by Zn P, and when you substitute these values, this comes out to be 0.101 Weber. So here you have to see this N has to be in the radians per second, because you have this is RPM, you want to convert it into the appropriate units, so please see about the units. So this comes out to be the flux per pole phi comes out to be 0.101 Webers. Okay, so this is that, and then we can calculate the specific magnetic loading, which is BAV is P phi over pi dl, and this comes out to be 0.938 Weber per meter square. So this is the specific electric loading and specific magnetic loading for this problem. Okay, so moving on, let's try another problem. You have a 125 watt 230 volt 5000 rpm motor, universal motor. It has a full load efficiency of 50%. You have to find out the power. You have to calculate the power developed in the armature if the constant losses are 1/3 of the total losses. So how do we solve this? We know that the efficiency is output power divided by output power plus losses, right? So if this is 0.5 and my output power is 125, then 125 plus losses, this is the total losses. So total losses come out to be 125 watts, and the constant losses are of course 1/3 of this, so this comes out to be equal to 42 watts. So the power developed in the armature PA is equal to the output power plus the constant losses. This comes out to be 167 watts. Okay, so this is the problem. This is the solution to this problem. So I encourage you to solve some more problems, and both unsolved and unsolved problems from the book, and I hope you will practice them, and if you face any problems, you will let me know. Now moving on, how do the linear dimensions or the changes in the linear dimensions affect the output and the losses of the machine. So we see that a relation of output okay. So what we do for this, we considered we have two machines. So we say that we have two machines which have the linear dimensions in the ratio of x is to 1. Okay, they have the same speed, they have the same flux density, and they also have the same current density. So what is different? The linear dimensions. This x is to 1 is the linear dimensions. So we have to see how these the change in the linear dimensions affects the output and losses of the machine. Okay. So we have machine A, and machine B, where linear dimensions of this machine A are x times the linear dimensions of this machine B. Okay. So let's see first the output. Q, the output, is directly proportional to BAV times d square L times N. This is the output equation. Since this BAV and the speed are constant for both machines, and there is this term AC as well, so BAV and speed is constant, so you have the relation, the output is directly proportional to specific electric loading AC times d square L. Okay, and now if you go to the equation for AC or the specific electric loading, it is this. So IZZ you can get from the current density times area times Z over pi d. So here you see that this linear dimension, there is a square of the linear dimension in area, and there is one in this the denominator, two powers in the numerator and one power in the denominator. So what happens, this AC, we can say that AC is directly proportional to x square over x, or we can say that AC is directly proportional to x, the change in the linear dimension. So what happens because of this, you have AC being directly proportional to x, and then you have this d square directly proportional to x square, and L directly proportional to x. So what is the outcome? The output is directly proportional to x times x square times x. So in effect this means that the output is 4 times the x raised to the power 4. So the output of machine A is x to the power 4 times the output of machine B, where machine A has linear dimensions x times the the linear dimensions of machine B. So this was about output. Next we talk about losses. let's see how we figure out what happens to the losses. Now if you see the I square R loss, I square R loss is a factor which depends on the number of conductors into the amount of copper in each conductor. I mean the copper loss in each conductor, right? So this is Z times Iz square rho L by Az, right? Number of conductors into the I square R loss of the conductor. So if you further see this, this is delta times Az square rho L by Az. So what is this? What does this actually translate to? The I square R loss is delta square rho Z Az into L, right? So this is delta square rho times volume of active portion of the conductors. Because area into length is the volume, so that's how we derive this relation. So what happens in this case? The I square R loss is directly proportional to the volume of the conductors. Why? Because this term is a constant. Current density and the number of poles are constant, and the resistivity are constant. This is rho, this is rho. So therefore the I square R loss is directly proportional to the volume of the conductors, so it can be concluded that it's directly proportional to x cube of the conductor. So the copper loss of machine A is x to the power 3 times that of machine B. Okay, so this is the copper loss. What is the other loss in the machine? The other loss is the iron loss. So iron loss, you must be aware that iron loss depends on the flux density. So if flux density is constant, there is no change on the iron loss. So what happens to the total loss? The total loss, which is equal to iron loss plus copper loss, then we can safely say that this total loss is directly proportional to x cube for two machines with difference in linear dimensions. Because this iron loss is constant, we only have the copper loss, which is a variable. And to conclude, we will see what happens to the efficiency. Now efficiency is the output over output plus losses. So we have seen earlier that output is x to the power 4, and this is x to the power 4 plus kx to the power cube. So then we can derive this. So if you have two machines with linear dimensions having a ratio of x, you can say that the efficiency increases as x increases, because this x is in the denominator. So this brings us to this conclusion that larger machines are are intrinsically more efficient than smaller machines. Of course, so if you see fractional horsepower motors, they have an efficiency of around 60%, while as large turbo generators, turbo alternators, they have efficiencies of around 98%. So this is, from this it's clear that the larger the machine, the more efficient it's going to be, given that the parameters such as the speed, the flux density, and the current density are constant. So if you have two machines which have linear dimensions in the ratio of x is to 1, you can say that we have seen that this output is x to the power 4 times that of the other machine. The losses are x to the power 3 times that of the machine. The iron losses are also x to the power 3 times the other machine, and the efficiency, we can assume, we can deduce that the efficiency is larger or higher for the machine having larger dimensions. And we also mentioned that these fractional horsepower motors, they are about 60% efficient, and in contrast, the large turbo alternators, they are around 98%. They have an efficiency of around 98%. So this was some brief idea about the basics of these rotating machines. I will need one more lecture to discuss some more details in this before we go on to armature windings. So in the next class we will talk about some more fundamentals before we go on to actually reading about design of rotating machines. So I encourage you once again to solve some more numericals and more problems, and I will see you in the next class, and I hope you see this video before the next class so that you are actually able to better understand and appreciate this course. Thank you.